Unit 6A deals with fluids and related topics. Fluids are a special class of materials that move continuously and deform when we exert a force on them. In other words, we would say that fluids have the characteristic of flowing. They take the shape of their container and they obey the laws of gravity and other forces. Solids, on the other hand, if we just put them on the ground, they stay intact. They don't take the shape of their container. They don't flow, so solids would not be considered fluids. Density describes the amount of mass contained within a given volume of material. So density, which we use the letter rho for, is the mass divided by the volume for some substance or fluid. Since it has mass over volume, the standard units of density are kilograms per meter cubed. And so in this example, we have a pile of feathers that is the same weight as a pile of bricks on the other end of this seesaw. The force of gravity pulling down on these feathers is just enough to balance the seesaw so that it's equal to the force of gravity acting on these bricks. But the feathers take up a lot more volume, and that's because they have a lower density. The bricks take up less volume, have a greater density, and therefore a greater mass in that small amount of volume. The table to the right shows you densities for some common materials. We spoke a little bit about pressure in our last class covering ideal gases, but pressure is a very important idea for fluids as well. Pressure is the amount of force divided by the area. Pressure has the standard units of pascals, and as a reminder, 1 Pascal is equal to 1 Newton per meter squared. Pressure is important for fluids because it will cover ideas like swimming underwater or medical applications like giving a vaccine or a shot. In this example with the vaccine, we can see that if you poke someone with your finger, that is a force that you exert with a pretty large amount of area covered. But if you poke someone with a very, very small area, like that of a syringe, it exerts a much greater pressure and can overcome the pressure of your own skin. Pressure is measured in a lot of other common units as well, so you'll want to know how to convert pressure from pascals to units like atmospheres, millimeters of mercury, torr, or PSI. Hydrostatic pressure is the first kind of special pressure that we will deal with, which involves a pressure being felt for an object that has more fluid above it. The reason why this comes about is because if you have more fluid above you, you're feeling a greater weight of that fluid above you at that point. So hydrostatic pressure is the pressure exerted by a fluid that's not moving when we think about the force of gravity that's acting on the system. The equation for the hydrostatic pressure is mass times the gravitational constant times the depth of the fluid you are at. So you measure the depth of the fluid from the top down to your reference point. And all of us are living under a hydrostatic pressure right now because of the fluid, the air that we are surrounded by. There's so much air above my head right now that I feel the downward pressure from all of that force of gravity acting on the top of my head and on my shoulders. This pressure that we feel at sea level is a very common value, so we give it the unit of atmospheres. And 1 atmosphere, the pressure that we live at right now, is 101,325 pascals. And when we measure pressures, we always make these measurements between 2 different pressurized systems. It's impossible for us to ever have a system that has totally 0 pressure. So we need to be very careful about when we're measuring pressure, thinking about what we're actually measuring. For example, we could use a device called a manometer to measure the pressure in a system. If we leave this manometer, which is a U-shaped tube filled with water, if we leave this open to the atmosphere, it will have equal amounts of force pushing down on both ends of it. So there's no difference in the 2 water levels in both sides of this column. However, if we put a balloon on one end and we squeeze that balloon, now we'll create a greater pressure on the right side, and that will cause the water in the manometer to move and equal out to have some difference in height between these 2 water levels. And that difference in height is a hydrostatic pressure, and we can measure it with a gauge. A gauge pressure is what we measure from a device like a tire gauge or a manometer. It can be positive or negative, because if we think about a system that's at lower pressure when we make these measurements, like this vacuum sealed jar of peanuts, if we put the column into that tube, it will suck some of the air out to equilibrate, and there will be another difference in the height of these 2 water columns, but it'll be on a different side. And that means that there must have been a negative pressure, a pressure lower in the peanut can than there was in the outside atmosphere, so that the atmosphere pushed down harder than the jar of peanuts did. Now we can specify a difference between the outside atmospheric pressure and the gauge pressure measured in some specific system, and this is how we make pressure measurements. The total of the gauge pressure and the atmospheric pressure is called the absolute pressure. The absolute pressure measures the sum of pressures from all different sources, and this absolute pressure can never be negative. So when you measure your friend's blood pressure, or in medical systems where they're measuring the ability of your lungs to press out air or the pressure in your eyeball, these are all examples where we would be measuring a gauge pressure. And here we presented the common pressures that you might measure on a gauge for many physiological processes in humans. So we can now think about pressures that are acting in fluid systems, and these pressures get greater as we go to lower depth. This gives rise to a concept called buoyancy. The buoyant force is the net upward force that acts on an object submerged in a fluid. So if you have an object in a fluid, it will always have at least some buoyant force pointing up. The buoyant force is what causes objects to sink or float. If the buoyant force that's pushing up on an object is less than the weight of the object itself, then this object will sink. And if the buoyant force is greater than the weight of the object, then the object will float. The equation for the buoyant force involves the density of the fluid, how much volume of fluid was displaced, and the gravitational constant g, 9.8 meters per second squared. Buoyancy occurs for all kinds of objects like anchors sinking to the bottom of a pool, a boat floating as it sails on the water, and helium balloons that are submerged in air. Another important idea for fluids is Pascal's principle, which states that a change in the pressure applied to a closed system will always spread itself out throughout that system. So if I have this fluid contained in this piston right here, and it's completely closed off to the environment, it makes sense that if I push down on one end, the other end would feel a force up. It just so happens that we can make use of this pressure idea by manipulating the area of these two ends of the piston. If the areas are different and the pressure is transmitted completely throughout this enclosed fluid, then the forces that act on these two different areas will also be different. And this is the idea that has applications in hydraulics and braking systems and jacks. In equation form, Pascal's principle is shown here. The ratio of the force to the area for each side of the enclosed fluid will always be equal to each other. Most of our diagrammatic models up to this point have been building so that we can create a full model for any physical system. Fluids is our first example of that. So there are many cases where you could use motion maps, force diagrams, energy bar charts, momentum diagrams, and other diagrammatic models to help you represent fluid systems. And here's a couple of ideas just for a few. Pressure diagrams are a lot like system state diagrams and energy bar charts. They display a fluid system with all the relevant variables listed. So far we've only learned about hydrostatic pressure, so you have to list the height. And then we also have a bar chart that keeps track of the different amounts of pressure relative to each other. So here I have all hydrostatic pressure in this system. At the reference point that I've set, H equals 0 as the bottom of the container. And remember, some pressures like gauge pressures can end up being negative, so you'll want to include a negative area in these axes. Force diagrams are also a useful way of looking at fluids. You can think about a fluid itself as being individual volume cutouts of that material. Then you can think about the forces that are acting on that material, including the force of gravity from itself interacting with the Earth, as well as the force of gravity from other cutouts of the fluid above that piece that you're looking at. So this is just our first preview of fluids. We're going to be talking about these for the next 3 weeks, so keep making sure that you're looking for them in your daily lives, and I'll see you next time.